Ground fault protection is generally not mandated on a 208Y/120 volts service due to the characteristic of the 120 volts line to ground voltage being unable to maintain an electrical arc. The underlying reason for this lies in the voltage level necessary to sustain an arc, which typically hovers around 30 volts. Since the 120 volts line to ground voltage remains below this critical threshold, the likelihood of a sustained arc fault is significantly reduced. However, this does not preclude the occurrence of ground faults at 120 volts. It's crucial to recognize that even without the presence of a sustained arc, ground faults can still manifest themselves in diverse scenarios. These scenarios can encompass factors such as physical damage to wiring, loose or compromised electrical connections, or, most concerningly, instances where a person inadvertently comes into contact with a live wire. To mitigate the risks associated with ground faults, ground fault circuit interrupters, or GFCIs, are employed. These devices are specifically engineered to safeguard against ground faults by meticulously monitoring the current balance between the hot and neutral conductors within a circuit. When a disparity in current levels is detected, exceeding a predetermined threshold, the GFCI promptly responds by tripping, effectively severing the circuit and halting the flow of electricity. This rapid response mechanism is instrumental in preventing potential harm or damage resulting from ground faults. Building codes and electrical standards mandate the installation of GFCIs in specific locations where the risk of ground faults is heightened. These locations typically include areas prone to moisture or dampness, such as bathrooms, kitchens, and outdoor outlets. The rationale behind this requirement is to provide an additional layer of protection in environments where the likelihood of electrical accidents is elevated. Furthermore, GFCIs can be implemented on other 120-volt circuits, even those not explicitly mandated by code, to furnish enhanced protection against ground faults. This proactive approach can contribute significantly to overall electrical safety within a building or facility. In summary, while ground fault protection may not be a mandatory requirement on a 208Y/120 volt service due to the voltage limitations in sustaining an arc, the potential for ground faults at 120 volts remains a valid concern. Ground fault circuit interrupters offer an effective means of mitigating these risks by swiftly detecting and interrupting ground faults, thereby minimizing the potential for electrical shock or fire hazards. The National Electrical Code, or NEC, provides comprehensive guidelines regarding the installation and application of ground fault protection. Article 210.8 of the NEC specifically addresses ground fault circuit interrupter protection for personnel, outlining the requirements for GFCI protection in dwelling units and other locations. It's essential to consult the latest edition of the NEC for the most up-to-date information and requirements related to ground fault protection. Article 215.9 of the NEC covers ground fault protection of equipment. It stipulates that ground fault protection of equipment shall be provided for solidly grounded wire electrical services of more than 150 volts to ground but not exceeding 1000 volts phase-to-phase for each service disconnecting means rated 1000 amps or more. The operation threshold is typically set at 30 mA, but it can be adjusted within a range of 5 mA to 30 mA. The maximum trip time at the ground fault pickup current is 1 second. Ground fault protection systems work by monitoring the current flow through all conductors of a circuit. In a balanced system, the current flowing into the load should equal the current flowing out. If there is a ground fault, some of the current will return through a path other than the intended circuit conductors, such as through the grounding system or a person's body. This imbalance in current is detected by the ground fault sensor, which then trips the circuit breaker, interrupting the flow of electricity. Equipment ground fault protection is designed to protect equipment from damage caused by ground faults. Ground faults can cause overheating, arcing, and other problems that can damage equipment and create fire hazards. Equipment ground fault protection is required for certain types of equipment, such as large motors, transformers, and switchgear. The requirements for equipment ground fault protection are specified in Article 230.95 of the NEC. Personnel ground fault protection, on the other hand, is designed to protect people from electric shock. It operates by detecting very small imbalances in current and tripping the circuit very quickly. This minimizes the amount of time that a person is exposed to electric shock, reducing the risk of serious injury or death. Personnel ground fault protection is required in locations where people are likely to come into contact with electricity, such as bathrooms, kitchens, and outdoor areas. The requirements for personnel ground fault protection are specified in Article 210.8 of the NEC. Understanding the difference between these two types of ground fault protection is crucial for ensuring electrical safety. Improperly installed or maintained ground fault protection systems can be ineffective or even dangerous. It is always best to consult with a qualified electrician to ensure that your electrical system is properly protected. The sensitivity of a GFCI is carefully calibrated to detect even minute differences in current. A typical GFCI trips when it senses a current imbalance of 5 mA or more. This level of sensitivity is crucial for protecting people from electric shock, as even a small amount of current can be dangerous. The speed at which a GFCI trips is also critical. GFCIs are designed to trip within a fraction of a second, typically within 25 milliseconds. This rapid response time minimizes the duration of electric shock, reducing the severity of potential injuries. The location of GFCI protection is dictated by the NEC and is primarily focused on areas where there is an increased risk of electric shock, such as wet or damp locations. Bathrooms are a prime example, where GFCI protection is required for all receptacles serving the countertop areas. Kitchens also require GFCI protection for receptacles serving countertop areas, as well as receptacles within 6 feet of a sink. Outdoor areas are another common location for GFCI protection, particularly for receptacles that are readily accessible. This helps to protect people from electric shock while using outdoor appliances or tools. Beyond these mandated locations, it is often advisable to install GFCIs in other areas where there is a potential for exposure to moisture or dampness, such as laundry rooms, basements, and garages. This proactive approach can significantly enhance electrical safety throughout a building. It's important to note that GFCIs are not a substitute for proper wiring and grounding practices. They are designed to provide an additional layer of protection in the event of a ground fault, but they cannot prevent ground faults from occurring in the first place. Regular inspection and maintenance of electrical systems are essential for ensuring overall electrical safety. This includes checking for damaged wiring, loose connections, and other potential hazards. If any problems are detected, they should be addressed promptly by a qualified electrician. The testing of GFCIs is also crucial to ensure that they are functioning properly. GFCIs should be tested monthly by pressing the test button on the device. If the GFCI does not trip when the test button is pressed, it should be replaced immediately. It's also important to understand the limitations of GFCIs. GFCIs are designed to protect against ground faults, but they do not protect against overloads or short circuits. Overloads and short circuits can cause fires and other hazards, so it is important to have proper overcurrent protection in place, such as circuit breakers or fuses. In addition, GFCIs do not protect against electric shock if a person comes into contact with both the hot and neutral conductors simultaneously. This type of shock can be just as dangerous as a ground fault, so it is important to avoid contact with exposed electrical wires. The proper selection of GFCIs is also important. GFCIs are available in different classes, each designed for specific applications. Class of GFCIs are the most common type and are designed for general purpose use. Class B GFCIs are designed for use in industrial applications and have a higher trip threshold. Class C and Class D GFCIs are designed for use in specific types of equipment and have even higher trip thresholds. It's important to choose the appropriate class of GFCI for the application to ensure proper protection. The installation of GFCI should always be performed by a qualified electrician. Improperly installed GFCIs can be ineffective or even dangerous. A qualified electrician will ensure that the GFCI is properly wired and grounded and that it is functioning correctly. In addition to GFCIs, there are other types of ground fault protection devices available, such as ground fault relays and ground fault monitors. These devices are typically used in industrial applications to protect equipment from damage caused by ground faults. Ground fault relays are designed to trip a circuit breaker when a ground fault is detected. Ground fault monitors are designed to provide an alarm when a ground fault is detected, allowing personnel to take corrective action before damage occurs. The use of ground fault protection is an essential part of ensuring electrical safety. By understanding the principles of ground fault protection and following the requirements of the NEC, it is possible to minimize the risk of electric shock and fire hazards. Regular inspection, testing, and maintenance of electrical systems are crucial for maintaining electrical safety over time. Always consult with a qualified electrician for any questions or concerns regarding electrical safety. This discussion highlights the nuances of ground fault protection, emphasizing the importance of understanding its limitations and proper application. By adhering to established codes and best practices, a safer electrical environment can be achieved.